half. So in BGP 102, we're going to talk about BGP policy. We'll talk about some common BGP policy implementations. And then we'll talk about traffic engineering and affecting the path selection. And we'll look at this both from a provider standpoint as well as from an edge network standpoint. After that, we'll look at BGP scaling techniques. We'll talk about route reflection and confederations. And if time permits, we'll do some BGP mechanics. So BGP policy. ISP customer route filtering, the best common practice is to filter customers by prefix. So in theory, you know what addresses you've assigned to your customer. If they're bringing addresses from an RIR or from another provider, they should tell you what addresses they're bringing, and you should check them to make sure that they're actually authorized to use them. Typically, this can be done by looking at the SWIP records or the RWHOIS. However, in practice, it's often much more difficult than this sounds. Some customers, you can imagine, have tens of thousands of entries in their prefix list. Sometimes they update 1,000 at a time weekly. Even worse, you may have customers that have downstream customers that have a direct allocation from an RIR. So in this case, it's virtually impossible to prove that your customer A has a downstream customer B. Sure, you can prove that downstream customer B has the right to use IP address 1.2.3.0/24, but how do you prove the relationship between customer A and their downstream customer B? Typically, this is done by a letter of authority that says, I am customer B and I authorize customer A to route my space, and customer A then sends it to their upstream transit provider. But I mean, that's as easy as faking as letterhead is, so it's not a very good system. Beyond that, there's also been some near misses. You can imagine that you might have a customer that is Banks of America, and somebody in your NOC doesn't look very closely, and they read Bank of America, and they go, sure, we'll route them the Bank of America space. We've actually seen some cases of that. You can also imagine that a branch office calls up and says, yes, I am Bank of America, please route this space, and you can look it up and it belongs to Bank of America, and you route it, and then an hour later, Bank of America calls you and says, why are you hijacking our space? And you say, you told us to route it. And they said, who told you to route it? And you said, oh, it was John Smith. And he says, oh, he's in our branch office in Iowa. This is corporate space. The branch office doesn't have the right to use this space. So it can be fairly difficult in practice to actually know ahead of time what prefixes a customer should send you. You can try to peer through an internet routing registry, and this can be helpful if it's kept up to date and accurate. Some ISPs, instead of doing prefix filtering, will do AS path filtering and use max AS. On the peer space, it's even more difficult to know what routes a peer should send you. If you're a large Tier 1 ISP and you're peering with another large Tier 1 ISP, it's impossible to know what all their downstream customers are. It's the same problem space as a customer with downstream customers, but just on a much larger scale. And oftentimes, peers aren't going to want to reveal their business relationships with their downstream customers. So typically, the filtering that peers will put on other peers is they'll restrict RFC 1918 space. This is the non-routable space, like 10/8. Sometimes they'll also filter bogons. Bogons is the space that aren't actually in use yet. They're unallocated space. Maintaining a bogon list can be problematic because space that was not allocated yesterday could be allocated tomorrow. So you have to be on top of that bogon list and keep it accurate, and if you don't, you're potentially filtering new people from the internet from reaching you. The last thing people look at is filtering internal trusted space. This could be as small a list as the loopbacks of all of your routers and your critical infrastructure like your Radius and TACAX servers. It could be even larger to include other internal infrastructure like your corporate network, but it is definitely not all of your IP space because some of that IP space is in use by your customers who may be multi-homed, who may want you to be the backup path and you want to be able to reach them over your peer. Some peers will do AS filtering. In this case, if you're a Tier 1 ISP, it's fairly easy to guess who the other Tier 1 ISPs are. And you could assume that another Tier 1 ISP shouldn't be giving transit to reach you. Another thing that's important from a policy perspective is ISP route aggregation. All of your static customers that are using more specifics of your IP space don't need to be advertised to the internet. Certainly you as a provider need to carry around those more specifics so that you can route traffic to them, but you don't have to tell the rest of the world. The rest of the world only needs to know how to get to your aggregate. BGP customers that are connecting only to a single upstream AS, if those customers are using IP space that's more specific of yours, again, this doesn't have to be advertised to the entire internet. Again, you need to carry around the more specifics internally, but if it's part of an aggregate of yours and the rest of the internet knows how to reach the aggregate, that's good enough to send the traffic to you, and then you can forward it down to your customers. In terms of route aggregation, the goal here is to offer a stable aggregate for your ISP space. You also want to keep the internet routing table small, so if you can advertise a single aggregate and that covers hundreds or thousands of customers, then that's good for the internet table. But you don't want to suppress more specific routes of static customers that are using their own space because they're not part of your aggregate, which means they're not reachable through your aggregate. And you don't want to suppress multi-homed customers, that is customers that are connected to your AS and another upstream AS, because they may need for you to advertise these more specifics to make their traffic engineering work. So typical of route aggregation implementation. Generally you create what's called a pull-up or tie-down or pin-up route, and that's a static route for your aggregate, usually pointing to null, zero, or discard, and you redistribute that into your BGP. Generally you don't want to place these pull-up routes on the edge routers, because if an edge router gets isolated from the core of your network, it will still advertise the aggregate and still draw traffic, even though it has no reachability to anything. So generally you want to put it in the core of your network, and in terms of which core router to put it on, generally you want to put it on all of your core routers, so that way if some portion of the core of your network is intact, you'll still advertise the aggregate, and that route will be stable and persistent. So generally the way you do this is, in addition to having your pull-up route or your tie-down route, you also maintain a prefix list of all of your aggregates. And you match on more specifics of that prefix list when redistributing from static or connected into BGP. And when you send routes to eBGP, you match on this community and you do not permit those routes being advertised. You can also do this for BGP customers if you know that they're singly homed only to you. Generally, there's not a good way to know if they're only connected to you or if they're connected to you in another upstream. But one way that you can do that is if you're using RFC 2270 ASNs or private ASNs for customers that are connected only to you. You can match on those ASs in the AS path, and if they're more specific than your aggregate, you can tag them with the community to suppress them on eBGP. So traffic engineering. In BGP policy, there's three basic flavors of traffic engineering for multi-homing. There's best path, primary backup, and load sharing across multiple links. Beyond those three basic configurations, there's the added dialing traffic around to draw more or less traffic in those three basic scenarios. And obviously you can combine all of these scenarios into very complex cases. So best path. So the requirements here is you basically want to use a non-random best path for reachability on the internet. The current best path is based on routing information based on the BGP path selection algorithm, which we talked about in the previous section. And it approximates the shortest path to the destination. And this is the default behavior. Primary backup requires the ability to designate one link as primary and use that for all of your traffic. And if that link fails, or if those sets of primary links fail, then you'll fail over to the backup links. The common reason for a primary backup configuration is because one link is more expensive than the other. And expense could be measured in various different units that may or may not be important to you. It could be the cost of the links. It could be the latency of the links. It could be the performance, packet loss, available bandwidth. So depending upon what metric is important to you, you might optimize to say prefer a low loss link over a high loss link. It's usually configured with local pref if you have two different upstream ASs, or you could use MED if you have a single upstream AS. Finally is load sharing. Load sharing basically requires loading traffic on all of the links, and the goal is to generally use all of your links as evenly as possible without having negative impact on the traffic flows. The common reason for load sharing is to try and squeeze as much bandwidth out of possible out of multiple links, and this is often the case in some markets where it's hard to get large capacity or large capacity is very expensive. You could imagine the case where you are in South America, for example, and you're trying to get multiple connections to upstream transit providers in the US. Those links tend to be very expensive, and you don't have a lot of choice about large links. And typically the way you accomplish this is by slicing up your prefix into shards and advertising different shards on different links. So let's take a look at some of these in the real world. ISP best path TE. So in this case, we've got AS1, and you can imagine that AS1 is some community college, for example, and AS1 is getting transit from AS701 and from AS2. You can imagine AS2 is a local university with which they have a relationship. And AS2 is getting transit from AS3. You can imagine AS3 is a university, a consortium of universities. It provides a network for multiple universities to connect to each other, and it also provides connectivity to the internet, which it does through AS4, which is a Tier 2 ISP, who gets transit from AT&T, AS7018. And 701 and 7018 peer with each other. So now the question is, in this configuration, how does traffic from AS5 reach AS1? So AS5 forwards its traffic to AT&T, and AT&T by default is going to break on shortest AS path and send it to 701 UUNet, who's going to send it to AS1. This is the default behavior. But the question is this the behavior that AT&T wants? Is it better for AT&T to deliver traffic to its peer or to its customer, AS4, who delivers it to AS3, who delivers it to AS2, who delivers it to AS1? So some things to think about in this space. If it delivers the traffic via its peer, it's a shorter AS, probably a shorter path, probably better service. If it delivers it via its peer, it's more likely to be chosen by people that are multi-home to AT&T and another upstream provider. If AT&T is sending paths that have shorter ASs in the AS path, it's more likely that AT&T is going to be used as opposed to the other transit provider, assuming the customer is getting best path. Also, peer links are generally larger than customer links, and peering contracts usually require that bandwidth upgrades happen when they reach capacity. However, on the other hand, customers pay the transit provider for traffic. Peers don't. So if you send it towards the customer interface, then the customer is paying for that traffic. Whether it's a metered service, or it's a tiered service, or it's a price-protected service, the customer is paying for that. And if you send more traffic down that link, if it's metered, certainly they're paying more. If it's not metered, if they're paying a flat rate, if you send enough traffic down that interface, they're going to have to upgrade from a T1 to a T3, from a T3 to a OC3, and et cetera. And all of that is more money. Also, peering points can sometimes get congested, and sometimes it's very difficult to actually get your peer to upgrade those capacity in those peering points. So going through a peer might not actually provide the best performance if there's congestion. Generally, most Tier 1 ISPs prefer customer routes over peers. So let's look at how this works. So in this case, AT&T sets a policy to lower the local preference on peers to 80. So any routes it learns from 701, it lowers the local pref to 80. Customers have a default local pref of 100, which is the default local preference. And because of that, AT&T will prefer customer routes over peer routes. So in this case, when AS5 sends the traffic to AT&T, he sends it down to its customer AS4, who goes through AS3, through AS2, delivered to AS1. It's also worth pointing out that typically providers that do this will offer communities to their customers to modify the local preference. So it's possible that AS1 could set some community to tell AT&T to make their local pref equivalent to what peers are, or even to make it better than what peers are, and either force it to go the other way or allow it to choose best. Outbound Tier 2 provider traffic local preference, same deal as Tier 1s, except they have an added level. Tier 2s generally prefer customers over peers, but they generally prefer peers over transit providers. And because transit providers, they're actually paying the transit provider to reach those destinations on the internet. So best path traffic engineering for end sites. So in this case, we've got a customer who's advertising its route to both upstream providers, in this case AS701UUNet and AS7018 AT&T. You'll note that he's advertising his entire address space over both lengths the same way, 1.2.3.0/24. And then each of these providers is going to announce the route to each other and the rest of the internet. So basically what's going to happen is the portion of the internet that's closer to AS701 will use AS701, and the portion of the internet that's closer to AS7018 will use AS7018. This is, again, the default behavior. For outbound traffic, the customer can learn full routes from both ISPs. In this case, it's going to use the upstream ISP that's closer to the destination. So for destinations that are closer to AT&T, it's going to forward through AT&T. For destinations that are closer to 701, it's going to forward through 701. You can also do this by advertising a default route as well. And in this case, it's going to round robin outbound traffic, so it doesn't really know whether the destination is closer to AT&T or closer to UUNet, because it's just learning a default route from both, and it's just going to take turns sending traffic to one and then the other without regard to where the destination is located. So this is kind of a load sharing outbound, which is the default if you're getting default routes instead of full routes. The other possibility is you may have some IGP metrics inside your local network, and that will cause you, if these links terminate on different routers, that will cause you to use the exit that is closest. So the left half of the network will be closer to the exit point to 701, it'll use 701. The right half of the network will be closer to the exit point for AT&T, it'll use AT&T. So local preference on the end site. So in this case, the end site basically wants to do a primary backup configuration. So in this case, it primarily wants to choose AS701 and only ever use AS7018 as a backup. In this case, he's going to advertise the same prefix to 701 and to 7018, but he's going to add a community towards 7018. And that community basically indicates that when AT&T learns this route, it should set a low local preference value. So 701 is going to re-advertise the prefix it learned to the rest of the internet and to AT&T. And AT&T has a policy that sets a local preference of 80 on all pure routes. So when that route is learned from 701 by AT&T, it's going to lower the local preference to 80. And AT&T has a policy that matches on this community, in this case 7018:70, and it's going to set local pref to 70, which is even lower than 80. So AT&T is going to choose best path, and when it does, it's going to prefer the path that it learned from 701 over the path that it learned from its directly connected customer. And that path is going to be re-advertised to downstream customers of AT&T. You'll also note that AT&T does not advertise the route that it learned from 701 to other peers, and that's because AT&T does not provide transit to peers. So you'll note the rest of the internet is going to use 701 to reach this customer, as well as customers of AT&T. They will also go through 701 to reach this customer. So for outbound traffic, they want to do the same behavior. They want to prefer AS701 for all outbound traffic, and only if that fails, use AT&T. So one way that this can be accomplished is they can receive a default route from both providers, and they can write some policy locally on their router for all routes learned from AT&T to set a low local preference of 90. In this case, for outbound, it will use AS701 to get to AS701 customers. It'll use 701 to get to the rest of the internet. It'll use 701 to get to AT&T customers. AS path traffic engineering. So in this case, AS1 is going to prepend its own AS 3 times towards AS701. So we see the route announcement is 1.2.3.0/24, and we see the AS path is 1, 1, 1, 1. So there's 3 prepends of AS1 plus the AS1 that's there naturally, which is why there's 4. So AS1 advertises to AS2 just the /24 with no prepending. AS2 advertises to AS3, who advertises to AS4, who advertises to AT&T. AT&T and UUNet advertise to each other as well as the rest of the internet. And now what happens is the rest of the internet, which is closest to AT&T, will use the AT&T links to get there. And the portion of the internet which is closest to 701 will use 701 to reach AS1. In this case, we're prepending only 2 times instead of 4 times. We get the same sort of behavior, but we've just shifted where the rest of the internet is closest to. So before, where the internet was, half of it was closer to AT&T and half of it was closer to 701. Now we have like 3/4 of the internet being closer to 701 and 1/4 being closer to AT&T. So in this way, we're drawing more traffic from 701 than we are from AS2. So there's some complications with this. Here I've now added AS5, who is multi-home to AS4, as well as to AS701. And if we prepend 4 times like we did before, AS5 is now going to prefer using AS4 through AS3 through AS2 through AS1. And that's not necessarily what we want. We might want AS5, who's directly connected to AS1, to go straight through AS1 to reach us. So one of the ways that we can do that is instead of prepending, we can send a community towards AS1. And that community will instruct AS1 to prepend its AS towards its peers. So here we show the route announcement. We're sending the /24 to AS1 with the community 701:3. And we're sending the /24 to AS2 just normally. So now AS701 is going to prepend 3 times towards the rest of the internet as well as towards AT&T. And AS2 advertises to AS3, who advertises to AS4, who advertises to AT&T, and AT&T advertises to the rest of the internet and to 701. So now you'll note that AS5, who's connected to AS701 and AS4 for its upstream providers, is going to prefer AS701. But the rest of the internet is unchanged. So as an alternative to actually prepending, you can send communities usually to your upstream provider and have them prepend on your behalf. And that will distance other peers, but not other customers. There's also this technique of poisoning a route where you prepend somebody else's AS. So in this case, the customer advertises a more specific route to one provider to draw extra traffic to that links with that provider. But in order to limit the propagation of that route, it might prepend another network's ASN. And this will prevent that other network from learning those prefixes because they will loop to that network. So as an example, we're advertising the /24 to both 701 and 701.8, but we're prepending 1239 Sprint in the AS path. And that's going to get announced to each other and the rest of the internet, and the piece of the internet closer to 701 will use 701, and the piece closer to AT&T will use AT&T. But then we've got this Sprint 1239 AS, which is not going to learn the route. So there's this cloud sitting here in the middle, which doesn't receive any reachability to the /24. And in addition, there's some portion of the internet that's downstream from Sprint that must use Sprint to get to the internet. They also have no reachability to this prefix. So why would you like to black hole Sprint from reaching this route update? Well, this might be part of a less specific route. For example, 1.2.3.0 might be part of the aggregate for AS701, in which case 1239 will see that aggregate. It might be, say, a /16, and it will draw the traffic. So this will actually swing more traffic over to AS701. But there's some danger in allowing people to prepend somebody else's ASN. And Tony Capella did a talk at DEF CON 16 in Las Vegas a while back and talked about this Capella-style attack, which is done by inserting somebody else's AS in the AS path and also injecting more specific hijacked routes. So I'm going to run you through a couple of his slides real quick to show you the dangers of this. So first, you do a man-in-the-middle attack and you observe what's going on. So in this case, the target ASN, AS200, is originating 10.10.2 220.0/22. And he's sending it to his two upstream providers, AS20 and 30, and they send it to each other as well as AS10, 40, and 50, and it eventually gets to AS60, and you see three paths to the attacker's AS100. And based on this routing information, you can understand how all of these networks are forwarding to reach AS200. AS20 is reaching AS200 through its directly connected link, same for AS30. AS10 is using AS20, 40 is using 30, 50 is using 30, 60 is using 40, and AS100, the attacker, is using AS10. Once you have this information, you then plan a replay path. This is the path that you want to preserve to make sure that you can return traffic to AS200 after you've done your man-in-the-middle attack. And then what you do is you hijack some prefix of AS200 that you want to be man-in-the-middle for, and you advertise that. And when you advertise that, you prepend AS10, AS20, and AS200 in the AS path, and you send that out to the internet. And AS10, AS20, and AS200 will always drop these updates because the AS path looks looped, but the rest of the internet will learn it. So AS10 doesn't learn the update, but 40 and 60 do, and 40 and 60 send it to 30 and 40, and 30 tries to send it to 20 and 200, and they don't learn it because the AS path is looped. So now what you've done is you've preserved the forwarding path from AS10 to AS200 and AS20 to AS200, but the rest of the network has been hijacked. They're all sending the traffic to you. And then what you do is you add a static route for the prefix that you've hijacked, and you give it a next hop of AS10, and you create a path back to AS200. So now for this portion of the internet, AS30, 40, 50, and 60, you're going to suck in traffic for that more specific route that you hijacked. You're going to do your man-in-the-middle attack. Then you're going to statically route it back to AS10, who's got a good path back to the target, who doesn't know that his traffic's been hijacked. So there's a lot of danger with that. That was the point of that. So moving on from AS path to MED. So in this case, we've got a customer who's got multiple connections to the same provider, and he advertises the same /24 across both of the links. If they're terminated on two different ISP routers, then each ISP router is going to use itself as its preferred path for itself and all directly connected customers. The rest of the network is going to break on IGP distance. So the portion of the network that's closer to the one exit point will use it. The other portion of the network that's closer to the other exit point will use the other exit point. And if IGP cost is symmetrical to both exit points, then it will pick just one exit point based on lowest router ID. So that's the default behavior. If it's terminated on a single router, it's fairly similar. But what's going to happen is the entire network is going to prefer that one egress router as the exit point. But once it reaches that router, it's only going to pick one link and load up one link and not both. Because on there's going to be two eBGP sessions here, and it's going to pick either the oldest path or the lowest router ID or the lowest neighbor. So not necessarily what you want. So if you, again, for traffic in the outbound direction, if you're learning a default route from the provider and it's terminated on two different routes on the customer location, each customer router is going to prefer its directly connected session, but the rest of the network is going to choose based on IGP path, or if IGP is equivalent, it's going to pick one router. So you end up only using one link primarily. So in this case, we've got, again, the default being advertised across two links. And again, it's a single router this time on the customer location, and again, the whole network is just going to prefer the one link. So you might want to do a primary backup configuration. So in order to do this, you advertise the same prefix in one place with a MED of 0 and in the other place with a MED of 10 on the backup link. And what will happen is for all inbound traffic, you're going to prefer the primary link and only use the backup link if the primary goes down. Same thing for outbound. You can learn a default route from both links, and you can write policy locally to set a higher med on the backup link. And in that case, you'll prefer the primary and only use that, and it only use the backup if the primary goes down. The other way that you can use med is, rather than setting it arbitrarily, is to mirror your IGP costs. So in this case, you've got some network here with another downstream customer, and you've got two different exit points to your upstream provider. And the cost from here to your exit point to the customer is 120, and from the other exit point to the customer is 650. When you go ahead and you advertise this /24 to the upstream, you can set a med of 120 on the left link and a med of 650 on the right link. So what that means is, no matter where the source is located, it's always going to prefer to come over this link, because that's the closest entry point to where the customer lives. Likewise, you might have another customer connected on the East Coast with different metrics, 680 to this exit point and 80 to this exit point. And you can advertise those prefixes with its meds as well. So now what's going to happen is, for any source in the transit provider's network, if they're trying to go to 1.2.3.0, they'll exit on the West Coast. And if they're trying to go to 2.3.4.0, they'll exit on the East Coast. ISPs using meds. ISPs generally don't manipulate meds of customer routes. Customers pay their transit providers to honor their traffic engineering preferences, and that often includes allowing customers to set med. So generally, transit providers don't muck around with meds on prefixes they learn from customers. Peers, on the other hand, don't pay, and peers generally aren't given the ability to do traffic engineering on a peer's network. So in that case, they usually flatten the meds and also strip off all communities. In some cases, there are some larger ISPs that force smaller ISPs to accept meds in order to qualify for peering. That's kind of in the contractual relationship. ISP IGP distancing. So ISPs typically design their IGP metrics based on network topology, usually some measure of distance, could be route miles, could be latency. And all things being equal, ISPs generally prefer to deliver traffic to destinations that are local to a given region, rather than through a remote region. And when they have to use a remote region, they usually like to use a remote region that's closer as compared to a remote region which is further away. So peers typically interconnect in multiple regions, and peers are typically required to send the exact same routes in every place that they connect. And an ISP can configure the interface facing the peer for a passive IGP and place a small IGP metric to push traffic away from an interface that's running hot. This is commonly called peer biasing. So let's give an illustration of what this looks like. Here we have 7018 AT&T and 3356 level 3. And you'll see that they're connecting on the East Coast in New York and Miami. And what you'll note is they're not connected in DC. So sources in the AT&T network that are in New York are going to exit out through the New York peering point and use the New York to New York link between AT&T and level 3 and deliver the traffic to level 3 in New York. Likewise, sources that are in the Miami region are going to exit out the Miami link to AT&T. The question is, what happens with the customers in DC? Sources in the AT&T network that are in DC, how do they reach level 3? Well, that depends. Is DC closer to New York or to Miami? Based on how this network was built and the IGP cost, we've decided that DC is closer to New York. So all of the DC region will use New York, exit out through the New York peering point, and go to Miami. However, it may turn out that that New York peering point is running a little bit hot. In that case, we can add a passive IGP metric of, say, 1,000. And that might be just enough to make DC a little bit further away from New York and a little bit closer to Miami. So in that case, DC may break and go the other way towards Miami and deliver all of its traffic to level 3 over the peering interface in Miami. However, the New York folks will still use the New York exit point, obviously, and the Miami folks will still use the Miami exit. There's also one other interesting thing to think about, and that's the case where the destination is multi-home to two peers that are connected in the same place. In this case, we can still add a passive IGP metric 1,000 and we can distance DC from New York towards Miami in exactly the same way. However, there's this set of destinations that are reachable both through AS701 and AS3356. And both 701 and 3356 connect in New York. So when we distance our peering point with level 3 in New York, the destinations that are multi-homed to UUNet AS701, those aren't going to swing down to Miami. Those are instead going to swing to the interconnect with 701. So what we see is that traffic moves down to our connectivity with 701 and gets delivered over that customer's link with 701. The DC traffic still does swing exactly the same way, and the New York traffic that is not multi-homed behind those destinations will stay where it was. N-site IGP distancing. So an N-site has equally good reachability through 2 upstream transit providers to a BGP destination. And this could be because both providers are sending a default route, or it could be that both providers are sending full routes and there's some set where the full routes are equally good through both providers. So if this terminates on a single customer router, then BGP path selection algorithm is going to break on either lowest or oldest path or lowest router ID. And if it terminates on 2 different routers, then each router is going to choose its own eBGP path as best, and the rest of the network is going to break on either IGP distance or lowest router ID. So if we look at this, basically what we end up with is half of the network could be IGP closer to one egress router, and half of the network could be IGP closer to the other egress router. So for outbound traffic, using a default, you're going to load up roughly half and half for half of the destinations on the internet. Again, if we were doing full routes, it would be the same thing, but we would only be talking about the set of routes that are equally good. And then what you can do is you can tweak your IGP metrics to make some larger portion of the network closer to one exit point. So by shifting things just a little bit, you can make, say, 2/3 of the network closer to the exit point on the left and 1/3 closer to the exit point on the route. Again, you can do this with full routes, but it's only going to shift the traffic for the routes that are equally good. Routes that are much closer to 701 or routes that are much closer to 7018 are not going to be affected because the tiebreaker is only for 2 equally good routes. ISPs advertising different routes. So ISPs often offer different sets of prefixes to their downstream customers. Some reasons for this is because the customer CPE might not have enough memory to take multiple full feeds of the internet, or customers might want to prefer a subset of routes for traffic engineering. So they might want to make one transit provider preferred only for customers of that particular ISP and make the other transit provider preferred for the rest of the internet. Or they could have some regional bias. The customer might be well peered outside of the Asia Pacific region and wants global customer routes only and only peer routes from Asia Pacific. So some options that are common from transit providers, full internet routes. This is everything that's in the provider's routing table except their internal more specifics. It includes all of the provider aggregates, all customer routes, all global peer routes, all regional peer routes, all routes for the local region, all national peer routes, all local country region, routes that they've learned from transit providers if it's not a tier 1 ISP, the entire routing table except the more specifics. Second possibility is full internet routes, but no transit routes. So if this is a tier 2 ISP that's buying transit from someone, give the full internet table except for the routes that they're paying to get transit for. Third possibility, full regional routes. If you connect to this provider in Europe, maybe you're only getting the European routes, for example. So you're not getting routes from Asia or North America. You can do the same thing on a national level. Could be just the UK. You might be getting UK customers and UK peers, but not all of Europe and not all of the global routes. You can also do no peer routes at all. So you can do all of the ISP's global aggregates and all of the customers connected to that ISP, but no peers. You can do a regional flavor of this where it's maybe the Asia Pacific region You could do a continental version of this where it's maybe just continental Europe, and you can also do a national version of this where it's, say, just UK, for example. And then you can also just get the ISP aggregates only. So this will get, all of the ISP global aggregates or regional aggregates or continental aggregates or national aggregates. It will get all directly connected customers that are using the ISP space, but it's not going to capture customers that have brought their own IP space. And then lastly, you can do any of those that I've described with a default route as well, or only a default route or no routes. So those are, some of your typical flavors that you can get from an ISP. N-sites advertising different prefixes. Oftentimes, N-sites will advertise more specific slices of their aggregate in order to get a more granular control over traffic engineering. So it's often used in conjunction with one of the other techniques that I already discussed, and then they advertise some additional more specifics to dial around some additional traffic to either move traffic away from links that are too hot or draw extra traffic to links that are running cold. It's important to note that smaller than /24, for example, a /25, a /26, those routes will typically be accepted by your upstream transit provider, but will not be propagated to the rest of the internet. So generally, if you're going to slice and dice your routes, try not to go smaller than /24. So primary backup. In this case, the customer wants a majority of the traffic to use the primary link, but they want some small amount of traffic to spill over to the backup link. For example, maybe the primary link is saturated. So what the customer will do is they'll advertise the aggregate across both links, and they'll advertise a community across the backup link for the backup provider to set a low local preference. And then they'll take some small slice of a more specific route and advertise that over the backup link to the backup provider to draw some traffic just to that set of destinations. In terms of best path, in this case, the customer wants the majority of traffic to use the best path. However, they want to nudge some small amount of traffic away from one of the paths that's overutilized towards another path that's underutilized. And the traffic that they want to shift, they don't want it to be arbitrary. They want things that are nearly as close to both upstream's ISPs to switch over to the path that's underutilized. So the way that they do this is they send some more specific route up to a /24 to both providers, and on the less preferred provider, they prepend it, in addition to the aggregates, obviously. Load sharing, in this case, the customer wants to balance traffic across multiple links, possibly of different sizes, and they want to advertise the aggregate to all providers over all links so that if there's a failure, they're covered. And then what they're going to do is they're going to slice and dice a whole bunch of different more specifics and advertise different slices across different links. And the size of the slice will control how much traffic they draw to a particular link. And the customer may also advertise these same slices on another link with a lower local pref if they want to control how things fail. So if they're advertising some small slice across one link, and if they want that link to fail and that traffic to go somewhere else specific, they can advertise that same slice with a low local pref across another link as well. So some other traffic engineering considerations, eBGP multi-hop. So this allows the BGP neighbor to not be directly connected. Typically when we think about eBGP, it's usually two routers that are directly connected to each other. Sometimes it could be a router further inside the network because maybe the edge router can't speak BGP. So that's a case where you would need to use eBGP multi-hop. It's also useful if you want to peer loopback to loopback. And what you could do is you could peer loopback to loopback and then use static routes to route across the links. The reason why you might want to do this is if you have multiple links terminating on the same router. So here what we have is we have two links between a pair of routers, and we're going to BGP peer between the loopbacks. So in this case, we're learning a default route from the transit provider, and the next hop is the loopback of the router that we're peering with, in this case 3.3.3.3. And in order to make that BGP session come up, and in order to figure out how to forward traffic, we put a static route on our CPE router for that loopback 3.3.3.3, and we specify the next hop to be both outgoing interfaces to that router. So basically what's going to happen is when traffic gets forwarded to this router to be forwarded towards the internet, we're going to do a round robin across both of these links. And if one of these links goes down, the BGP session will stay up because we're appearing with the loopback, and all of the traffic will slosh to the one link that's remaining. BGP multipath. In this case, what's going to happen is we're going to have two different BGP sessions on the two different routers, and each local router is going to prefer its local eBGP session for forwarding to the upstream ISP. In addition, each local router is going to pick one best path. If you recall from the path selection algorithm, eBGP is preferred over iBGP, so they'll each prefer their own eBGP path as best, and they will each advertise their best paths to each other as well as to other routers in the network. If this other router is configured for BGP multipath, say for example multipath 2, it will accept both paths. It will do path selection, it will pick one best path, and if it's doing say eBGP with another router, it will only send that one best path to the other router. However, when it goes to install the information in the forwarding information base, rather than only installing the best path, it's going to install multiple paths so long as the tiebreaker was lower than IGP distance. In this case, we have BGP multipath 2, so it will configure up to 2 equally good paths. So in this case, this router will forward to both edge routers. If we do a comparison of multi-hop versus multi-path, we'll note that multi-hop only works when all of the links are between the same pair of routers, and we must have only a single eBGP session. That single eBGP path has a single protocol next hop, and that next hop is reachable by equal cost static routes. Multi-path can work when the links are on different eBGP speaking routers in the local network. And we have a separate eBGP session for each link, and then we run multi-path on other routers that speak iBGP with the eBGP router. And it will have as many fib entries as there are discrete eBGP speaking routers that learn the path up to the number of the multipath, up to the number that's supported, which I think in most vendors is 16 nowadays. So there was one other technique, which is to use the IGP for equal cost multipath. In this case, we're again learning a default route across two different links from the provider with two different next hops, 5.5.5.5 and 5.5.5.1. And we advertise that to the iBGP. And some router in the network will choose one best path, say 5.5.5.1, for example. But if each of these edge routers both redistribute 5.5.5.1 and 5.5.5.5 into the IGP, and we have equal cost IGP distance to both of these routers, then we don't care whether we picked the next hop of 5.5.5.1 as best or the next hop of 5.5.5.5 is best. Whichever one we pick, we have IGP reachability to both edge routers, we'll forward to both edge routers, and we'll load them both up equally if our IGP is symmetrical. So the last thing I wanted to point out about traffic engineering is that it really is a complex layered approach. For example, you can imagine you want to do a lot of things. You want to have 1.2.0.0/24 to be the best path out of both of your providers. You want 1.2.1.0 to mostly be the best path out of most providers, but draw a little extra traffic over AT&T. You want 1.2.2.0/23 to be preferred over UUnet's primary links. You want 1.2.5.0/24 to be preferred over AT&T. And you want, if any of the 701 traffic fails, to use the 701 backup links, and if any of the AT&T bundles fail, to use the 701 backup links. So you can end up with some really crazy routing policy. I'll let you guys study this offline. It's quite interesting. So I wanted to move on to the next topic, which is BGP protocol scaling, and talk about iBGP route reflection and configuration. So just a quick review from the first part. You've seen some of these slides before, the differences between eBGP and iBGP. eBGP is when your neighbor is in a different AS. iBGP is when your neighbor is in the local AS. When you're running eBGP, every best path is advertised to your eBGP neighbor. And the protocol next hop is typically changed to be your neighbor address. When you run iBGP, if you learned a path via iBGP, you don't re-advertise it to the iBGP. and this requires a full iBGP mesh of peering, and the iBGP neighbors are generally not directly connected. You advertise every best eBGP path towards the iBGP, and you don't change the protocol next hop. So again, you've seen these slides before in the first half. Just to refresh you, we've got a /16 static route, which gets redistributed into BGP, and that goes to all of our iBGP neighbors. We learn that route on an eBGP speaking router. Because it's best, he sends it via eBGP from AS200 to AS100. AS100 in this case is setting next hop self, and AS100 re-advertises the /16 to everybody in the iBGP without changing the next hop. So the important point here is that when a router learns a path from one iBGP neighbor, it doesn't re-advertise it to another iBGP neighbor. So this requires that you have a full mesh of iBGP sessions in the network. So this can be quite difficult to scale. This is an n times n minus 1 divided by 2 iBGP sessions. So in this simple diagram of 12 routers, we have 66 iBGP sessions. And if you miss a single session in here, which is easy to do, you can end up with routing loops or black holing. Additionally, when you go to activate a new router, you're going to have to turn up hundreds of iBGP sessions on that new router and also touch all of your existing routers and add one session on all of them. And then from a protocol perspective, beyond a small number of hundreds of neighbors, it just doesn't scale. So how do we get out of this? We'll get to that in a minute. Let's talk about path implications. So if you hear a route from eBGP, that will be your best path, and you will re-advertise that to everyone in the iBGP. So that means every router in the network will see exactly one path for every place where the eBGP router terminates. If he terminates on 2 different routers, everybody in the network will see 2 paths for that route. So route reflection. The network topology often lends itself to hierarchy. For example, you may have edge routers, and those edge routers may be connected to hub aggregators, and those hub aggregators may be connected to core routers, and the core routers may have some dense mesh between them. This has a natural hierarchy to it. And rather than doing an iBGP full mesh of all of these devices, what you can do is you can just run BGP with the routers one level up who are reflecting routes back to you. So the edge routers become route reflection clients of the hub routers, and the hub routers become route reflection clients of the core routers, and the core routers, being at the highest level of the hierarchy, do a full iBGP mesh. So in terms of route announcements, basically what happens is when you learn a route from eBGP, you're going to send that to all of your route reflector servers, and they're going to reflect that path back down to clients as well as to non-clients. And then the route reflector servers that learn from non-clients will reflect those paths down to their clients. Route reflector servers do not reflect paths from non-clients to other non-clients, which is why you need a full iBGP mesh at the highest level of your hierarchy. And it's also worth pointing out that you can deploy these in hierarchy as well. So you can have a route reflector server who's a client of another route reflector server who's a client of another route reflector server. And this is all documented in RFC 4456. So clusters. Each route reflector server and all of its downstream clients form a grouping called a cluster. And each cluster has a unique number. If you have exactly one route reflector server in a cluster, you can use the router ID as the cluster ID, and that maps very easily. And that's the most common implementation. However, if you have more than one route reflector server in a cluster, then you have to come up with some locally unique numbering structure for your cluster IDs. It's important to note whether multiple route reflector servers are in the same cluster or different clusters, because if they're in the same cluster, they will not learn routes from each other, and this is for loop prevention. So let's look at how we construct this. So we have edge devices that are going to be clients of their upstream hub aggregators, and those upstream hub aggregators are going to be the route reflector servers. So in this case, we've got these 3 edge devices that are clients of these 2 hub aggregators. We've got the same thing on the other side. And then the hub aggregators are going to be clients of the core routers, who will be their route reflector servers. So in this region, we've got 2 hubs that are clients of these 2 core routers, These guys are clients of these two core, and these guys are clients of these two core routers. And then in the center, we do an IBGP full mesh, which is with a smaller number of elements and much more manageable. So what does this do to paths? Well, we learn one path from eBGP, and he's going to send that up to his route reflector servers. At the highest level of the hierarchy, we've got a full mesh. So in that highest level of the hierarchy, you will see as many paths as you have route reflector servers that are serving a router where this edge is connected. And then the clients will see as many paths as they have route reflector servers. So if this client has 2 servers, he's going to see 2 paths. So you're necessarily going to end up with more paths than you did with IBGP. So here we show the clients learning paths from their route reflector servers. So when a path gets learned via eBGP, he sends it to both of his route reflector servers. If this happens in 2 places, that's under the same pair of route reflector servers, they're only going to choose one best path. So you do get a little bit of path reduction here. Also, at the highest level, in this case, we have a full IBGP mesh. It depends on whether or not these route reflector servers are in the same cluster or a different cluster. So if you can imagine they're in 2 different clusters, then what's going to happen is, because these route reflector servers are part of the IBGP full mesh, they'll learn an extra path from each other. If instead we put them in a single cluster, they're no longer going to learn paths from each other, because even though the sessions are there, their own route reflector cluster ID is in the cluster path, so those are looped, and they'll throw them away. So if you want to minimize the number of paths, try to put all of your route reflector servers that are serving a set of clients in the same cluster. However, that's not always easy to do. So you can imagine here we've got this hub, which nicely fits into cluster 1, and this hub, which nicely fits into cluster 2. But what do we do with this guy that has remote connectivity to both? Well, one possibility is we put him in cluster 3, which means that these route reflector servers have to be able to support multiple clusters, which not all vendors can. The other possibility is we stick him in both cluster 1 and cluster 2, but this doesn't necessarily follow the physical, which up until now all of the topologies have. And this is a little bit problematic because it doesn't follow physical, more on that later. And it also increases the number of paths. This edge router now has 4 times paths instead of 2, and towards the rest of the network we have 4 times paths instead of 2. So the other way that you can reduce your IBGP full mesh is through confederations. And the way you do this is you create a sub-AS, and in the sub-AS you do a full IBGP mesh, and then between sub-ASs you do EIBGP mesh, which is enhanced internal BGP or enhanced interior BGP. Some people sometimes call it external internal BGP, which is kind of sort of right in terms of thinking about how it works, because it has some properties of internal and some properties of external. Another way it's referred to as CBGP or Confederate BGP. To the outside world, it still looks like a single autonomous system, and this is all documented in RFC 5065. So the rules for EIBGP announcements. Send all best paths to EIBGP neighbors. If a best path is learned from EIBGP, announce it to the IBGP. If a best path is learned from IBGP, do not announce it to other IBGP neighbors because you have a full mesh there. Append your sub-AS to the AS path length when advertising to EIBGP, although these don't count in the AS path length. They do count for loop detection. And strip all sub-ASs when advertising to eBGP. And don't change the next hop local preference or med values like you would on eBGP. So how do we construct this? Well, typically we take the routers in the core and place them in their own sub-AS. And then we take what's remaining and place those into their own sub-ASs and run eBGP at all the touch points. I'm sorry, EIBGP at all the touch points. So that's our typical implementation. In terms of paths, when an edge router learns a path via eBGP, that edge router will announce it via IBGP to everyone in the sub-AS. And each of the IBGP speaking routers will advertise one best path to the IBGP. And then the core routers are going to announce to the core iBGP mesh if their best path was learned from eIBGP. And it's important to note here how the IP addressing is done, because we have a bit of a race condition, and this router advertises first, and his IP address is 100.2.2.2.2. He advertises to the other router that learned eIBGP routes. This router is learning the same path from 100.2.2.2.2 and also from 100.2.2.3. Because 2.2.2 is lower than 2.2.3, the best path is the one that he heard from 100.2.2.2, which is the iBGP path. So naturally, the second path is going to be suppressed towards the iBGP in the core. So each of the eIBGP speaking routers will send one path to the local region. Again, we have a bit of a race condition. One of them advertises first, and then it depends on the other one whether his best path was iBGP or eBGP. In this case, we have the exact reverse numbering. So this router is learning from 100.2.2.11 via iBGP and 100.2.2.10 via CBGP or eIBGP. So the eIBGP path is best, and he also announces to the region. So some comparisons between route reflection and confeds. Always follow the physical. I alluded to this earlier. If you have route reflection servers, make sure that they're higher up in the physical architecture. And if you're doing confeds, make sure you configure eIBGP sessions between all the routers that have links to remote sub-ASs. If you have an inconsistent control plane and forwarding plane, it can be difficult to troubleshoot. And let's face it, how many of you can walk into your network operations system and ask your staff, do you know the difference between routing and forwarding? Do you understand when it's a routing outage that you have to go off in this direction and troubleshoot, and when it's a forwarding outage, you have to go off in that direction and troubleshoot? So at worst, your mean time to repair is going to double if you don't follow the physical. It also increases the number of failure scenarios because now you have discrete control plane failures that are different than forwarding plane failures. And if either of those happen, you're going to break your ability to use the network. And lastly, it can also cause path reduction, which may reduce some paths that are better for some part of the network. So if we look at this in the route reflection case, in this case, we've got the same remote hub here, but we've made him only clients of cluster 1. So he's got this route reflection client relationship where there is a physical link and one where there's not a physical link. And then he's also got this physical link which has no BGP. So if both of these links go down, his forwarding is isolated and he's broken. But also, if the BGP process for these route reflector servers go down, he's lost all of his control plane and he's isolated, even though this link is still up. So this is how you increase your failure scenarios. You have the same problem with confeds as well. The other issue also is a reduction in best paths. So in this case, we can imagine that we just took our core routers and made them our route reflector servers. So everybody downstream from the core routers is a client, including the hub aggregators. So now what we see in terms of paths is customer 1, who's multi-home to hub 1 and hub 2, advertises to an edge router in hub 1 and hub 2. The hub 1 edge router advertises them up to the route reflector servers. The hub 2 edge router advertises them up to the route reflection servers. The route reflection servers are going to choose one best path and reflect that down to their clients. And it's going to be based on their view of the IGP. So in this case, the route reflector server is 110 away from this blue path with next hop A, and it's 610 from this red path with next hop B. So the route reflector servers are going to choose the blue path with next hop A as best, and that's going to be the ones that get reflected down. And as a result, this customer 2, who's connected to a different edge router in hub 2, instead of going up to the hub aggregator and back down, it doesn't see that path. It only sees the path with next hop A. So it has to go all the way up and wrap around and deliver from hub 1. So confeds, you have the So in this case, we've got customer 1 who's doing eBGP to hub 1, and those routes are being sent via the iBGP full mesh to the eIBGP speaking routers. And he's also doing eBGP to hub 2, and those routes are sent via the iBGP full mesh to the same pair of routers. These routers are going to choose best path based on their view of the IGP. So the cost to get to customer 1 is either 10, or it's either 30 plus 10, 40. So 10 is obviously better. So only this blue path is going to get announced to the core and to the other regions. So this means customer 2, when forwarding traffic, is going to forward it via hub 1, even though it's got this express shortcut path here. This express shortcut path is only going to be used to deliver traffic to customer 3, who's not multi-homed, and not to anything that's multi-homed to hub 1. So this is a case where the path reduction hurts you because you lose best paths by not following the physical. If you did CBGP on these links, everything would be taken care of. So some other comparison between confeds and route reflection. Route reflection is more commonly used. Migration to route reflection is easier. Both provide a convenient place to do configuration for routing policy for geographical division. So if you make your boundary between, say, countries or continents be CBGP or route reflection servers, that's a very convenient place to put policy to do route containment to keep stuff on continent. Both reduce the iBGP full mesh. Route reflection necessarily increases paths as a number of the route reflector servers, which you may or may not care about depending upon how much RIB memory you have. And the increase of number of paths can be managed with confeds through careful IP numbering. Confederations can also be used in a migration where one network is swallowing another. In this case, you can make the other network a confed of the local network and then swallow it up and then eventually integrate it. And if both networks are doing confederations, you can simply remove the eBGP session between them and put eIBGP sessions instead, assuming that you have non-overlapping sub-ASs and you've configured both networks to be aware of the entire list of sub-ASs. And you've unified the IGP, obviously. So the other thing I referenced in the first half was this med oscillation issue. I talked about how on Cisco routers it only does a pairwise comparison of the paths, and you can have a bit of a race condition and end up with a non-deterministic behavior. And I said I would talk about that with respect to med oscillation in a hierarchical network where it's much worse, where you get this persistent loop. So basically what you have here is you have 3 paths where route B is better than route A, and route C is better than route B, and route A is better than route C. And like I said, this can occur in a flat network where you have Ciscos that are doing pairwise comparison, or if you have Junipers configured with Cisco non-deterministic meds, but it's not persistent. Here is the persistent case in a hierarchical network, and the example I'm using is route reflection. So the network first learns a path with a next hop of A, and that gets advertised via eBGP from AS3, and that gets advertised to its route reflector servers. And this route reflector server is a client of the next route reflector server. And we can see in his routing table that we've learned the single path which is best with the next hop of A, with an AS path originated by 1 behind AS3, with a med of 10 and an IGP cost from his view of 20. And that floods out to the rest of the network. Then secondly, we learn a path for B. So via eBGP, we learn the path from B on our egress router. We advertise that to our route reflector server, who's a client of another route reflector server. And when he does that, this B, next path with next hop B, this green path becomes best. And because the blue path, next hop A, is no longer best, it gets retracted. So once this path gets advertised to this route reflection server over here, we see it show up in our routing table. It's a new path. We do new best path selection, and they both have the same neighboring AS, and we see med of 10 versus med of 0. Med of 0 is better, so that becomes our new best path. We retract that from our upstream route server, and we advertise that the new best path to our downstream route reflector server. And when our downstream route reflector server learns it, A is no longer the best path. That gets retracted, which disappears from our routing table, and that continues to flood across the rest of the network. So now we have path C, which comes in here red in this case. And we learn C via eBGP on this edge router, and we advertise that to the rest of our network. And C is better than B, and this route reflector server chooses C as best, so it sends an update to its downstream clients to say C is now better than B, and it sends an update to its upstream client, in which case we learn the new path, and we do path selection, and now we choose between B and C, and we'll note that B has an IGP cost of 100 and C has an IGP cost of 30, so C is better. So we retract our route for B and we advertise C towards our upstream route reflector. In this case, there's no change because the IGP metrics are flopped the other way because we're on the other side of this link, which is cost 80. But now that B has been withdrawn, A now becomes best. So we advertise A to our route reflector server. When we learn it here on this route reflector server, we now compare between A and C. And we see that A has a lower IGP cost than C, 10 as opposed to 20. So A is better. So we select A as best, and we're back at our starting point. You can see how we've cycled through. And this will keep going until routers reach 100% CPU and crash. Right. So I guess we've got a few minutes left. Wanted to do some kind of low-level BGP mechanics, talk about the state machine. The first thing that's worth pointing out is that BGP uses TCP port 179. This was an important improvement over eBGP because it's reliable. It has a three-way TCP handshake. It has session numbers. It deals with flow control. It deals with retransmits. And it also provides support for TCP MD5 signatures for security. In terms of BGP, which going down one layer deeper, it has 4 different types of messages. It has an open message, and when it sends the open message, it signals its BGP capabilities, which is the version it's running, like version 4, whether it can do IPv4 unicast, IPv4 multicast, IPv6 unicast, IPv6 multicast, labeled IPv4, labeled IPv6. They agree on timer values and authentication type. And this is all determined at the time of the BGP open, so you can't change these capabilities later after you've established the session without tearing the session over and starting over. So each neighbor will present a set of capabilities. To the extent that they overlap, they will agree upon the overlapping capabilities. If they don't overlap at all, if one router says, I support IPv6 unicast, and the other router says, I support IPv4 multicast, they have no overlap, then the session will just never establish. The second type of message is an update. This is how a BGP router signals that a prefix is being added, a prefix is being withdrawn, or a prefix is being modified. It's important to note that this is an incremental update, so once the entire routing table is flooded, you only have to send changes to that table, unlike EGP, which was a complete flood every time. And then attached to a prefix in an update are the attributes which I talked about earlier, the AS path, the origin, the communities, etc. The third type of message in BGP is a notification. And this is basically one neighbor telling the other neighbor, hey, something went critically wrong. You sent me some kind of message that is clearly broken, that I didn't understand, and I'm giving up. I'm tearing down this session, and I'm going away, and you can start all over once you figure out what's broken on your side. So typically what will happen is if a bad update comes through, when the router processes the bad update, it'll go, oh, this is bad. It'll throw the update away. It'll generate a notification to the far side, and it'll close the TCP session, and then they'll start all over again. And if the router is in a state where it's got some bad hardware, where this problem is persistent, it'll come back up, make all the announcements. Once it hits this bad one again, the far end will send another notification and close the session down. So you can see sessions bounce up and down and up and down and up and down because of this. And the last type of a packet is a keep alive. If there's a lot of network churn and updates are very regular, there's no need to send keep alive messages. However, if the network is very quiet and there's no need to send updates, then it will send keep alives just to keep the session alive to make sure it doesn't time out. So I referenced a little bit BGP capabilities. Here's the table of all of the capabilities, which you can reference on iana.org. I'm not going to talk about all of them, but I'll pick one or two that I think are important. The first one is multi-protocol extensions. And this allows BGP to support more than just plain old vanilla IPv4 unicast. Basically, it has AFI and SAFI. AFI is the address family identifier, which is either IPv4 or IPv6. So AFI1 is IPv4 and AFI2 is IPv6. And then it has subsequent address family identifiers, which describe which types of IPv4 and or IPv6 are supported, whether it's unicast, multicast, unicast and multicast, MPLS labeled VPN. And this is how they have extended capabilities to BGP version 4 without having to do another version. BGP capabilities route refresh. So once you establish a BGP session and you've learned a whole bunch of updates, you might decide that you want to go in and change your BGP policy. You've decided that the bogon route filter has changed and now suddenly something that was bad is now good, or for some reason you want to change what your policy is towards a particular customer or peer. The problem is when you change the policy, it doesn't necessarily take effect immediately. It's only going to take effect for new updates. So you're going to have to wait for some instability and for that route to either be withdrawn or updated before the new policy is going to take effect for that particular prefix. So one way to get around this is to configure soft inbound reconfig. And basically what that does is when you learn a set of prefixes from a neighbor, rather than just processing them and storing them in your RIB, what you do is you first store them in a RIB-in before you do any processing. And that consumes memory, and it's very expensive, and it's very hard to scale if you're a Tier 1 ISP and doing lots of BGP with peers. So a lot of the Tier 1s don't do this. And as a result, so if you do this, though, you can change policy and then just take everything that's in the RIB-in and reprocess it through your new policy. As an alternative to this, in order to not consume all of this memory, people said, well, why don't we do this route refresh capability? Why don't, when the BGP message gets exchanged, the routers indicate that they can support route refresh, and in the event that they can, after you apply new policy, you just send a message to the far end saying, hey, I applied new policy, can you just send me all of your updates again, even if nothing has changed? And the far end router will generate all the updates and send them through, and those will hit the new policy, so that way you don't have to wait for the route to churn or be withdrawn or updated. So that's route refresh capabilities. Another one is graceful restart. Basically, routers indicate that they can continue to forward packets when the routing capability stops. This is sometimes called nonstop forwarding, and it's useful when the BGP process restarts or when you're switching from a primary RP or RE to a backup RP or RE. So if your route processor dies and you have to switch from primary to backup, you can probably still forward based on the stale information. So what happens is when the BGP process restarts, it notifies the neighbor of the restart. The neighbor marks all of the state as stale, but continues to forward on it for a short period of time. And it requests a new set of updates while forwarding on the old state, which is marked stale and made less preferred. So as the session starts to come up, new updates start to come in. Once you learn the entire table because you have an end of RIB marker, and once your IGP is reconverged, then you push those new updates to your forwarding information base and begin forwarding on the new information. And then the old stale information will just age out. So one of the last things I wanted to talk about is the BGP state machine. So I wanted to just do a quick walkthrough of this to give you an idea of what you're looking at when you first bring up a neighbor or when you go to troubleshoot a neighbor. It'll start off in the idle state, and idle is the process is doing a lot of housekeeping, setting up the ports. It'll open up a TCP session, and it'll listen for responses for a TCP session. Either side can send the open first. There's kind of a race condition, so either router can be kind of the one who starts the TCP session. So you have to both try to open your own TCP session as well as wait for the remote end to open one with you. Either can happen. As soon as you attempt to open the TCP session, you go to the connect state. And in this state, you're waiting for the TCP session to be established. You're still listening for them to establish a TCP session with you. And you send a BGP open message once the TCP session is established and move to the sent state. If for some reason it times out or it doesn't progress, you're going to fall back to an active state. Once you're in the open sent state, you're going to listen for the BGP open message, and you're going to check to see if you've received open messages that are valid and that you have compatibility match up. So if one side says I can do V4 and the other side says you can do V6, you're incompatible, you give up. You could have other issues with it. It could be the wrong AS. You could be expecting to peer with AS1 and the far end says they're AS2, in which case you go, this is not going to work, and you give up. Or the far end might say, I only support BGP version 3, and you might say, I only support BGP version 4, in which case, again, you give up. Similarly, if you have the wrong MD5 password. So assuming you get an open message back and it's valid and you don't have an incompatibility, then you will proceed on to the open confirmed state. And in open confirmed, you're listening for either keep alives or updates. And once you receive either keep alives or updates, once you receive a keep alive, you move to the established state where you start sending updates and start receiving updates. And you have a BGP hold time typically configured to be 1/3 of your hello time. If your hold time expires at any time, either because you're not getting keep alives or you're not getting updates, you moved back to an idle state. The active state is when you're restarting your TCP session. So if you're in the active state, you basically tear down TCP and start over. And if you can do successful TCP establishment, then you move to the open sent state. And if not, then you go back to an idle state. So those are the sort of states that you'll cycle through in the BGP state machine as you're trying to establish a BGP session. Some advice on BGP configuration. Use templates. Peer groups are fantastic and templates are great. Have a standard set of policies that you can apply to all customers, to all peers, to all transit providers. Apply policy even if there's no function to perform. If you're blindly accepting every route and you're blindly sending every route that you have, it's still a good idea to put a policy that permits everything. Why would you do that? Well, at some point in the future, you may want a policy that modifies what you're sending or what you're receiving. And if you establish the neighbor without any policy to go and put policy on after the fact, is going to cause the session to bounce. However, if you have an empty placeholder policy there, then you can change the value of that policy without bouncing the session. It's also good for your support staff to get comfortable with the fact that there are policies in place, where to find them, what they're named. Peer groups. Peer groups are fantastic. Originally, the idea behind peer groups was if you built a peer group and put a whole bunch of neighbors into that peer group, you could build a single set of updates and have a single rib out for that peer group and save a lot on CPU and memory. In reality, it doesn't really help that much because all of your neighbors in the peer group are not in lockstep with each other. They're all in different point in terms of where the updates are being processed. So you end up building updates for all of your neighbors anyway, so it really doesn't save you much from memory and CPU perspective, but it's great for being able to organize and manage your peers. You build your peer group once, you set your policy for the peer group once, and then you just add particular neighbors to your peer group for customers or for transit or for settlement-free peering. Even consider having separate peer groups for classes of neighbors, even if they have the same policy. For example, you might want to have the same peer group, you might want to have different peer groups for transit providers as well as peers, just because at some point in the future you might want to have divergent policy for those two sets of BGP neighbors. So that'll give you greater flexibility later without having to move a set of neighbors out of a peer group, causing the session to go down. Another consideration worth thinking about is this TTL hack. By default, eBGP has a TTL of 1 because you're expecting the routers to be directly connected. And when you're peering loopback to loopback, this is why you have to set eBGP multi-hop 2 in order to make the session come up, because you're changing that TTL. In terms of a cheap way to do security, some people thought, well, what if we set the receiving router to expect a TTL of 254 and set the transmitting router to have a TTL of 255? So this means when the packet is put on the wire, it has a TTL of 255. When it gets received by the ingress router, it decrements to 254. that means the only person that can ever send a packet to this ingress router is somebody who's directly connected. So somebody 2 or 3 hops away can't even manage to send a TCP packet to the router, because they would have to set a TTL of 255, and by the time it goes through two or three hops, it's already a TTL lower than what you're accepting on ingress. So certainly something worth considering. Another consideration is route damping. Initially, people thought this was a great idea. The intention here was to reduce stability. So what happens is when a route flaps, you basically penalize it, and as it flaps increasingly more rapidly, you start listening less and less to those updates. So eventually you penalize it and you say, I'm not going to listen to you for a while because you flapped so much. Figure out what's going on, stop flapping, and then I'll start listening to you again. In reality, most people don't use it anymore. People don't use it with their customers because their customers are paying them to accept their routes. And people don't use it with peers or transit providers because it actually causes more harm than it does good. A single flap can cause a downstream AS to experience multiple flaps as each network calculates a new best path and floods the updates. And even within a single network, the updates can take different amounts of times to move through the network, and you could have different race conditions. So it's very possible that a single flap could be recorded 3, 4, or 5 times. So you end up over penalizing people for flapping. So for this reason, route damping actually tends to reduce stability and increase CPU load, and tends to make destinations unreachable for a long period of time. So generally people are moving away from it. So we've got about 3 minutes left before the member meeting. Questions, concerns, observations? Well, thank you for your time. I'll be hanging around here for the next little bit if you want to come up and ask me anything in particular.